Okay, so let's remember a little bit the integration for calculus 1. So for calculus 1, so we define an integral on the interval a and b, no? A and b, right? And let's say that f is a continuous function. You have a continuous function like this, right? So what you used to do, so how do you find this the area below the a and b? Okay, that was what we used to call this integral between a and b of f of x is this thing, right? That was the idea of integration. And so what did we do? So what we did was that was ab, and when they take the difference b minus a divided by n, so depending how many intervals you want, let's say n is 10, so you want 10 intervals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And this guy was called delta x. Okay. And then for each interval, so the idea was always to do this, right? So we're gonna make rectangles like here, 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 and here. So the idea was to find the area of each rectangle and add their areas. And the limit when this number n goes to infinity will make smaller rectangles, so the area will get closer to the real. Okay, so that was the idea. So what we did was to choose a point. So you can choose a point in the middle. Okay, and then we said, okay, so if this is delta x, what is the area of this rectangle? The area of the rectangle is base times height. And the base was delta x, and times the height, let's say this is xi, so the height is f of xi. So let's call it the star. So this is times f of xi. So this guy is the area of this rectangle over here. Okay. And then if you make the sum of all the rectangles, that's what was called the Riemann sum. Okay. And when you take the limit, when n goes to infinity, that means more rectangles, 1,000 instead of 10, 1,000 or 1,000,000, you get a better approximation of the integral. Okay. So basically, this limit sum with this delta x, that's what it means, the integral, dx. Okay. That's the real meaning of the integral. Okay. The limit of the infinite sum. Okay. Also has the meaning of the antiderivative, but anyway. But now we're in calculus 3. So we're gonna integrate over a rectangle. We're not gonna integrate over the line, but over a rectangle. Okay. So then you need two intervals, AB and CD, right? Now, and this is what is called the Cartesian product. So this is what is called AB cross CD. This thing means all this. Okay. And now, so instead of making a division like A and B like this, we're gonna make a division like that. So again, this is just to explain to you where is the integration coming from. But you're not gonna do this ever again. So I'm gonna go kind of, I don't want to skip this because it gives you an idea. But really what we're gonna do is do integral. So don't be scared, trying to pay as much attention as you can. But at the end, we're not gonna use this that much. But what is important here is that this guy is gonna be called delta A. That is the area. So instead of having delta X, it was delta X, we need delta A because this is the, instead of having interval, we have rectangles or squares. And now we need to choose one point here, we call it f of xi, right? So we're gonna choose the point, for each rectangle, we're gonna choose a point. Oh, and we're gonna call it xij star j star ij. So because it moves from 1, 2, 3, 4, 5, it's one row and column. So this is rows and these are columns. Okay. So you need 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4. So it's like 24 points. Right? That's why you need this enumeration, row and column. Okay, that's just notation. And now you're gonna find, oh, I don't have that nice drawing. Okay, I have it here. Look at this. So you're gonna, for each square, you're gonna make how do you call that? Print? That's a print? How do you call this? Yeah. How do we call it?
Rectangular prism.
Huh?
A rectangular.
Prism. Okay, thank you. A rectangle prism. Okay. So instead of having rectangle like this in calculus 1, in calculus 3, we have this one, because what we're gonna do is for each point here, we're gonna make a rectangle. So let me see, how can I make a nice rectangle? Maybe I just need to try it. So maybe like this. Okay. So how high it is f of ixj's. Okay. So for the volume of each rectangle prism, how do I do? I need the area of the base, that is the delta A, times the height, and the height is the function, right? Because I'm gonna have this base here, and I'm gonna have the function on the top, like this. So I'm making a prism, and then it's gonna approximate the volume. So when make the sum of all those prisms, I'm gonna get an approximation of the volume, of below this function. Okay. So I'm finding the volume below of the graph of the function. So that the double integral is the volume below this function. So the double integral of f of xy dx dy is going to be my integral between AB and CD. So this is AB, this is CD. Okay? That's important. And something that we're going to do sooner or later is prove that the volume of the sphere is 4/3 PR cubed. That you have been using since high school and you don't know why. So, thanks to this double integration, we can prove that. Okay, and we will. Okay. So I make the long story a little shorter, but you see, this is the sum, the sum, finite sum. Then I take the limit. But look at this. This is the double limit. This is, it's nasty, double limit. So limit and then limit. Okay. And this delta could be different, but we're saying we're not going to complicate our life. So we're just making the base of the rectangles all the same. Okay? And that's the definition of of this integral. So what is R? R is the region. So R is this. This is R. This is my region. In this case, is A, B cross C, D. Okay, that's the rectangle. Okay. We could do this simulation. We could do this example, but I'm not gonna do it now. I wanna try to go right away to integration. Okay, because this is just integrate one variable and then integrate the other variable. So this is again, this is just calculus 1. So this is n equals 4, n equals 15, that's n infinity. And here this is the three-dimensional case. And this is n equals 10, n equals 10, m equals 10. So that means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then on I'm gonna divide this side in 10 parts, and I'm gonna divide this part in 10 times 2. And then I make my when n is equal to infinity, I get the volume. Okay. But so let me skip down to, so what are the properties of integration? So that the sense that you expect, let me make sure this is recording. Yeah. So what are the properties of integration? They are the same that you knew before. Remember on integral, you knew that the integral of f plus g dx equals integral of f dx plus integral of g dx. The same thing. You can add them. If you have a constant, you can take the constant out. Okay. And if this function is bigger or equal than the other function, then this integral is going to be bigger than the other integral. Okay. Well, those we discuss later. So let's see we can make an exercise. We'll do in a second. So let's go directly to evaluate double integrals with iterated integrals. Okay. So this is the same that calculus 1, but do it twice. Okay, so it's not. But since we have been working on the derivatives, the partial derivative with respect to x, partial derivative with respect to y. So that's what I want to go right away to this. Because this is similar. When you integrate with respect to x, y is constant. If you integrate with respect to y, x is constant. Okay. So this is kind of, it's gonna help you to understand all these ideas again. So I want to do an integral. Let's do this example. And then I will come back here to this, all this review. But I want to give you a feeling of what we're gonna do, like go right away to work. Okay? Okay, so we're gonna find this integral, guys. So important. This could be the easiest exercise of your exam. So the region is 0, 3 to 4. So what does it mean? X is between 0 and 3. No. 0 and 3. And 2 and 4. So let's say this is 2 and this is 4. So the region is like this, right? So I need to find what is the volume. So if I make it 3D, that looks something like this, and my function is something over here. How does it look? You need a computer for that. You know, those are not that easy to plug in. Okay. So, but doesn't matter, because all that I need to do is this. integral between 0 and 3. And an integral between 2 and 4. So of xy plus 6y squared. So question, what should I put first? Should I put dx dy or should I put dy dx? So 1 or 2? How should I write that down? Dx dy, let's see. So x moves between 0 and 3. So, but the first one is 2 and 4. So this one goes with this one. Okay? So no, it has to be the other one. So it has to be dy dx. It has to be dy dx. You could, if you want to write dx dy, you have to change the order integration. You can do 2, 4, 0, 3, xy plus 6y squared dx dy. Okay? Well, that's how you learn, yeah.
So it doesn't matter if you like switch the numbers, it will give you the same.
But if you switch, you need to switch here. Right? But later we're gonna learn that it's possible to switch for good reason. Well, actually it's here. It's called Fubini. It's called Fubini Tonelli. Okay, so this is what it's saying. We can switch. What happens is that this example is easy because it's a rectangle. When you are gonna switch, you have to be careful. But this is usually good. If the function is continuous, you can switch. But if the function is not continuous, you can't. If the function is not nice, you cannot really do that. Okay. So what we're gonna do. So let's do these ones between 0, 3 and 2, 4. So we're gonna do 1. Okay, so be my guest. Find me the first integral with respect to y. So let me give you 5 minutes to do that one. So let me put an announcement. So the last day to drop the class is June 27, okay? After June 27, dropping is not permissible. So let me put that here. The announcements. Okay, so let's do it. So I'm gonna integrate So I leave the 0 and 3 and the x like that, right? So I need to integrate with respect to y. So what is the antiderivative of xy? Because I integrated with respect to y. So what is the antiderivative? Or the integral of xy with respect to y?
X Y squared over 2.
Xy squared over 2, correct. Plus 6, what is the integral of y squared with respect to y?
2y cubed.
Say again? Oh, yeah, so y cubed over 3, right? And this has to be evaluated between 2 and 4. Okay? So I need to evaluate on what? On y, right? So I have integral between 0 and 3, and then I guess x is 4 squared divided by 2 plus 6 4 cubed divided by 3 minus, and then you evaluate the 2. 4x divided by 2. Make sure you put your minus in parentheses, right? Minus parentheses. 4x divided by 2 plus 6a divided by 3. And this is dx, right? Sorry, let me put my dx over here. This dx goes over here, right? So I don't have a space. So I got 4 times 4, 16 divided by 2 is 8, right? So integral between 0 and 3 of 8x. 4 times 4 is 16 times 4 is 64. Times 6 divided by 3. Oh my goodness. 6 times 64 divided by 3. So you guys can help me with that. Oh, well, no, it's not. 10, 1, 1, 2. Okay. So it's 128. Right? And then what did we do here? So I plug in 4, 2, 4. Oh yeah, that's correct. Then I got minus 2, 2. I got minus 2x. And then it's 6 times. Okay, third 1, third 2, that's minus 16 dx. Correct? So 8x minus 2x is, what is it? 8x minus 2x, 6x. And 128 minus 16 is 112 dx, right? So now I need to integrate this with respect to x. So then I integrate. So what is the derivative integral of dx of this? So you see the y disappeared. Okay. So if I integrate with respect to y, the y need to disappear because I evaluated between 2 and 4. So I integrate with respect to x. What do I get? 6 squared divided by 2. Six squared divided by 2 plus 112. What? X between 0 and 3. So I evaluate 3. So when I evaluate 3 is 3 times 3 is 9, 9 times 6 is 54. Divided by 2 plus 112 plus 3 is 336 minus 0. So this is half 27. So that's 356, 363. Yeah. So that's the volume. So there you go, you got the first double integral. Okay? Any questions? So, no questions? Okay, so let's go back a little bit into the theory. Because here, so basically we did this part, we calculated the integral. And so what we had done, so let's go back to what we had done. So you have C equals f of xy. This is this one, right? This is C equals f of xy. That's how a 3-dimension or what 2-dimension function look like when you graph it in 3D. Okay. And this is your rectangle A, B, C, D. Oh no, sorry, this I put it wrong. So sorry, this is X, this is X, it's AB, this is AB, this is CD. Also, just for the physicists, so physicists prefer to put the dx like this f of x sometimes. Just to signify, so you don't get confused who goes first. Okay, so physicists do stuff. So this is the volume, right, of this function. But from calculus 2, you learn something, right? From calculus 2, you learn that the volume of a 3-dimensional solid region. So you can also, there is another way to calculate the area of a ball of a 3D figure. This is calculus 2. So what you used to do? You used to make a cross section. Okay. That's the area of this guy. And then you move it from A to B. So you're moving. So this area, so it's that it doesn't make sense in because the volume of area is 0, right? But since you are doing an approximation, you are finding this volume. And when you move it from A to B, you find the volume of the whole thing. That was calculus 2. Yeah. Those dark days. Remember? Who took calculus in the spring? Who took calculus in the spring? Nobody? On the fall 2023. Who took calculus 2 in the fall 2023? Okay.
I took it in the summer.
The summer of 2023? Okay, so somebody before that? So you have to remember all this stuff, okay? So this is again, this is the volume. So to find the volume of this, we have to do volume is the integral between A and B, integral of CD of f of xy dy dx. Okay. Or you could do calculus 2, do the cross section here, find the area of this part, but then integrate this area from here, from this case, from C to D. If you want, but if you don't like that, well, I give you another option. Do the cross section like this. Find the area of this part, and find the integral between A and B. Okay? And so, you just do that's the amazing thing of mathematics. You can do either way, you're gonna get the same answer. Or you just find this double integral and it's the volume. So there are 3 ways to calculate this volume. Okay. For now. So I think this is okay. And now, as I was saying, we were saying, can we interchange the values? Yes. If the function is nice, the function must be continuous. If you have division by 0, for example, you have 1 over x plus y. If this is your f of xy, you have to be careful because if y equals minus x, you are divided by 0. So in this case, y equals minus x, let's say this is your domain, y equals minus x. Over the top of this line, you have division by 0, so something weird is gonna happen. So that's not a nice function. Functions are like, nice functions are the like parabolic, or the ones we talk, right? So ellipsoidal, spherical, right? But things that with division by 0 or a square root of a negative number, they're not nice. So we have to be careful when we do this changing. Okay. And then, I just did what we had to. So let's see. Now we need to find the volume of the solid region that lies below the surface. C equals x e to the x minus y. Okay. So go ahead. Let me give you 5 minutes to do this. Maybe only stop there. So tomorrow I'll do another hour, but before class. So I give you the 2 hours for the exam. Okay. But I'll do 1 hour before. So you please watch the video so I can give you more time for your exam. We want still not sharing. Okay, let's do it. So find the volume of the solid region that lies below the surface. So sometimes it's easier if you choose one integral or the other one. But this one is okay. You can do it either way. So we're gonna do integral between 1 and 2, an integral between 0 and 1 of x e to the x minus y dy dx. If you did the other order, that's fine. We will do the other order too. So that's fine. So either way, it's gonna give you the same. So if you do this one, something that we used to do to make our life easier is if you can split x and y, just split it. So for example, this one has x, this one has x, and this one has x, but I can split this one. So I'm gonna split this one. Look at what I'm gonna do. So integral between 1 and 2, integral between 0 and 1, x e to the x times e to the minus y, dy dx. So I'm integrating with respect to y. So what happened to x and e to the x? They are constants. So I'm going to take them out from the integral. So I got integral 1, 2, and then x e to the x, integral between 0 and 1. And then I got e to the minus y dy dx. And now I find my integral. What is my antiderivative of e to the minus y? What is it?
What?
Second?
Minus e to the minus y.
Minus, yes. Minus e to the minus y. dy dx. And this has to be evaluated between 0 and 1. Minus, yeah. This is y because substitution. So if you don't know why is this, do it by substitution. I'm not gonna do it because you do a lot of substitution in calculus 1 and then substitution in calculus 2. So this is integral between 1 and 2, x e to the x, and then I evaluate at 1 and minus e to the minus 1 plus e to the 0, that is 1 dx. So now I need to find the integral with respect to x. This is a number, so I'm just gonna take it out. So I don't have to worry about this. And this is minus e to the minus 1 plus 1, integral between 1 and 2, x e to the x dx. And then now we need to solve this integral. I'm gonna do it just for courtesy, but this is, how do we solve this integral?
Which by parts.
Integration by parts. That way you guys should be able to do this. But I'm gonna do it just to, to review a little. So let's do, I'm gonna erase here all this. Let's do it over here. So we need to find the integral x times e to the x dx. So I do u equals x, db equals e to the x dx. So if u equals x, what is du?
Yeah.
Dx. And what is b? E to the x. That's integration, right? So if I do this, it's u times b, so the integration by part is u times b minus integral of b du, and this is u db. So integration by parts means I'm switching this guy with this guy. Okay. So x u times b is x times e to the x minus integral of b du. So here is follow me. Okay, let me do it in this one here. So I was doing. Okay, so it goes like this. Okay. So I have one minus e to the minus one integral between 1 and 2 x e to the x, right? And then I did integration by parts. So, I already did it, so I'm gonna skip that part. So this is what we got. We got x e to the x evaluated between 1 and 2 minus integral of 1 and 2 e to the x dx. Now you evaluate, you get 1 minus e to the minus 1. You plug in 2 e to the 2 minus e to the 1 minus the derivative of e to the x is e to the x between 1 and 2. One minus e to the minus 1. You get 2 e to the 2 minus e to the 1 minus, and they go e to the 2 minus e to the 1. We get 1 minus e to the minus 1, 2e2 minus e to the 1 minus e to the 2 plus e to the 1. And so this cancel with this is 1 minus e to the minus 1, e to the 2, this cancel. So when you multiply these are just numbers, right? So you get e to the 2 minus e to the 1. That's it. Okay. So we did 2 integrals. And tomorrow I'm gonna do double integral, section 5.2, with different regions. So we're gonna integrate. So today we integrate over rectangles. Tomorrow we're gonna integrate over curves. Okay. By little, we are doing changing the level of difficulty. Then we're gonna do change polar coordinates, and then spherical coordinates, and then cylindrical coordinates. So we'll see how far we can go. I'll do my best to finish this chapter, but on Friday I need to start chapter 6 because I only have July 4 is a holiday, so I'm gonna miss one day. And chapter 6 is really the most important one. So this is kind of things we have seen before, like, but chapter 6 is really something different, new, very important for electrodynamics. Okay. Okay, guys. So I think you can. Well, I'm gonna let you open your quiz, your sample exam. So you can start with your sample exam. So I'm gonna let it open now. I think I said 5, but let me open it now so you guys can start right there. Okay, so I'm gonna make I love this video, okay?